Okay, let's continue on in chapter 4. And again, we're not going to type these into the program. We're just going to talk about what they represent and so forth. Now, this is practice exercise 4.10, the Verilog. And over here is our definition of it. This is our, so we got an entity here, the inverse gate. And we've got B out standard logic and A in standard logic. And then we've got our architecture. Boolean equation of inverse gate is not A goes into B. So this is our kind of our defining inputs and outputs. And here's the actual implementation of it. Down here, again, this is our defining our inputs and outputs. So we got A, B, and C coming in, and D going out. And then the actual implementation of it's down here. So we got A and B and C, and then there's a not in front of it. So that's our NAND gate. And NAND 3 is because there's 3 inputs. Then down here, we got our, let's see. It's our A, B, and our enable coming in. Then we have our D going out. And it's a standard logic vector, range 0 to 3. Then structure of that is got a component, our inverse gate. Then we got our component NAND 3 gate. Our signal down here. So the G1, the inverse gate, got a port map, A not A. And the inverse gate is our component right here, which matches up above. Same for all those. The NAND gate look at the definition of that. It's 3 inputs, not A, not B, not enable, and then 1 output, or D0. Again, this you can think of this as an array is what it's doing. So that's our definition, our design of that particular decoder. over here, we have our A, B, and our E coming in. So those are our inputs. And then we have the knots right here. So that's what that pertains to. And then down here we have our NAND. So that's our AND with a knot on it. And that's what you see right here with this NAND. Does that make sense how that definition matches our figure? Okay. Like I say, we won't input that because it's probably not going to work anyway. With I don't know if it's a G's or what. I didn't get a chance to look that up to see what fixed it the last time. Now, hierarchical modeling. A hierarchical system can be composed of multiple design objects organized in a hierarchical structure. The hierarchy is formed by instantiating subcircuits within circuits. For example, an 8-bit adder can be formed by instantiating and connecting two identical 4-bit adders. A 4-bit adder can be formed by instantiating and interconnecting 4 full adders. And the full adder is declared twice, but it's instantiated and used repeatedly. And figure 4.33 shows a hierarchical structure of an 8-bit ripple carry adder. And figure 4.34 shows the functional blocks of the hierarchy and interfaces. So if you look over here, for example, an 8-bit adder can be formed by instantiating and connecting two identical 4-bit adders. These are 4-bit adders, I believe. 4-bit adder can be formed by instantiating and connecting 4 full adders. We've got our 4 full adders here. And they're just demonstrating that coming off here. Okay, that's about the extent of it there. Now, they're just indicating that once you design these one time, you can repeat it over and over. So you don't have to keep designing. It's kind of like the idea of a function where you're passing in different values. It's like the example over here where I'm defining the input and output here. And that then, what's coming in as the input output is specified down below. And you can almost think of it as its parameters coming in. This shows a different decomposition. So that corresponds to our top over here. And then that's going to go into one of these. For example, like this one here. We actually have 2 of them. I'm not sure why this says M0. It's not what it says on the previous page. Okay, those have nothing to do with the previous page. They start all these with the Sub-Zero, because that's M Sub-Zero, M1, and M Sub-Zero or M0, M1, M2, M3. So that really doesn't have anything to do with the M's you see over here. Okay, so then we have our breakdown of 4 there, corresponding with the 4 here. Then our half adder here. I see everything except for, like here we got our XOR and our AND, which is our XOR and our AND here. I'm not connecting this to the diagram on the previous page. Oh well. Okay, so on this, we're defining modules here. A half adder or a full adder. That corresponds here. Add underscore RCA4. Add underscore RCA4. The RCA8. This one right here. So they're breaking down these into modules that we can work with. Now the very lowest one here, our half adder, has an XOR and AND built in, and that corresponds to this right over here. So that's our definition of the half adder. Then our full adder, which is right here, has 3 inputs. That's this up here. It has 2 outputs, which is this and this. Wire, which corresponds to these W's you see here, W1, W2, W3. And then it's consisting of a half adder, add half, and another add half, which is there. And this one has A and B, and W1 and W2. So here's W1 coming out, and here's W2 coming out. That W2 is going into this half adder, which corresponds to the W2 you see right here. It's also having a CN. Where's the CN? Okay, here's the CN coming in here. And then taking away W3 and some. W3 is coming out here, and some's coming down here. Is that making sense so far? Okay. again, I think of it like a function. Here we have a smaller definition, and then this is a function that consists of these items before it. And then our RCA4, which is this right here, we're going to have 4 full adders, which means you have add full 4 times, M0 through M3. And again, you can think of this as like passing parameters. These are not the same as our parameters defined up here, but they map. And we're bringing A0, B0. Um, Maybe I shouldn't worry about details of this too much. What do you think should be there instead of A0? See how they have a G here? That's coming in to my full adder. The B0 is coming in, and the CN's coming in. So B0 is fine, CN is fine, but A0 is labeled as a G. I think they have that labeled wrong. I think that should be A0 there. Okay. I sure don't see word G comes in anywhere else. Then our next one, we have the CN1 coming in from here. That's our input. We have A1 and B1. So that all matches. CN2 comes out, and some 1 comes out down here. Then we have A2, B2 coming in, and we have CN2 coming in. And then we're having CN3 come out and some 2 come out. So all matches. Then our last one, we're having A3, B3 coming in, and then we're having CN3 coming in. So that matches. Our C out is like that, and our sum 3 is coming down like that. Yeah, G shouldn't be there. So I read later why they decided to label it as G and it's really A0. So then we have our RCA8, which is right here, which consists of two RCA4s, which is why we have two RCA4s here. And for this first one, we're bringing in A30, B30, and CN, and that's giving us CN4 out, and then it's giving us some 30 down to here. Our next one should have A74, B74, A74, B74. We're having CN4 come in. We have C out going out. And then we have our sums 74 coming down there. Okay, so that's pretty much everything except for this typo. What else was there? That's everything. Page 198. Verilog models can be instantiated within other models. Let's like create an instance of it. But module declarations cannot be nested. That is, a module declaration cannot be inserted into the text between the module and end module of another module. Also, instance names, M0, must be specified when a module is instantiated within another module. Now, a VHDL model of that RCA8, an 8-bit adder, constructs components for the logic gates in figure 4.34 and uses them in half adders and full adders. Once a full adder and a half adder are written, they can be used to create the RCA4 and RCA8. Okay, so they're going through and declaring all of the different components we have. We have the AND gate. We have the OR. In terms like our diagram here, that'd be the OR. Exclusive OR, which is right over here. And I guess that's all the different components. Then down here, we declare some entities, a half adder, and full adder down here, and RCA4 right here, and RCA8 right up here. Now a half adder. Remember what our half adder represented over here? It had the AND and the XOR. This tells us where we're bringing in and out. We have A and B and C out. And some. Oh, yeah. A and B for in, C out and some for out. So A and B coming in, C out and some coming out. Now that's our entity definition. Down here is our actual architecture. This is referring to that this structure is the AND 2 gate, which over here, our AND 2 gate, the Boolean equation of that is A and B. So again, this is our definition over here. And then we're referring to that when we're coming up with this. Then we've got our XOR gate here too. It's defined over here on page 198. And our XOR. It's just right here. We got A XOR B. Stand up just for a minute. Oh. Okay. So begin here. We define a G1. Then we use our XOR 2 gate. And A and B, and then some. Okay, that makes sense. Because A's coming in, B's coming in, and just sum's coming out here. So we're just looking at this little piece right here. The next one is the AND 2 gate we defined. So we got A, B, and C out. That's this little piece right here. So we got A coming in, we got B coming in, and we got C out. Okay, so down here to our definition of our full adder. A, B, C in. C out and some going out. Full adder. So A, B, C in coming in. It's throwing me how they have this labeled. I don't think it much matters. But they're saying the OR gate has an A and B coming in and a C going out. I see the C out coming out down here. But this is the OR gate they're referring to. I don't see A coming in or B coming in. It's coming in as wire 1 and wire 3. Well, like I say, maybe that's just the definition, and it's when we actually um, have our begin down here where it passes in what it really needs. So let's look down here. Okay, so we got an M0 half adder, and we got BCN coming in. Half adder. Let me go look at the definition of half adder. Okay, so this one right here, M1, is a half adder AB W1 W2. So AB coming in, W1 W2 coming out. Okay, see that? And the other half adder, B and C in. Excuse me. Okay, working it backwards. This OR 2 gate here. We got W1, W3, and C out. W1, W3, C out. Okay, I agree with that 100%. This half adder here, we have A and B, and then W1, W2 coming out. That corresponds to this one. So A and B coming in, W1, W2 coming out. This one, M sub 0, it says we have B and C in coming in and C out in some. C in's coming in, I agree with that. But I don't see B coming in, I see W2 coming in. And I see W3 and some coming out. Do you think that's wrong there, Director? Yeah, the circuit they show here is correct. But this doesn't seem like it flows correctly. Because they have B coming into both half adders. And B is not going into both half adders. It's just going into the first one. Now, if it went around also, See, because W2 would be modified after it went through this half adder. W2 would be a modified value. It wouldn't be the original B. Hmm. Oh well, I guess I won't worry about it. Bothers me it doesn't match though. Okay, that's our okay. RCA 4. Okay, so let me come down here to the definition. M0. That's our full adder right here. It should have A0 and B0, which it does. They got rid of the weird G they put over on that diagram and again replaced with A0 and B0. Should also have CN coming in, and CN's coming in there just fine. You should have CN1 coming out and some 0. So CN1 coming out and some 0. That's perfect. For M1, we should have A1, B1, CN1. So A1, B1, CN1 coming in. We should have CN2 coming out and some 1 coming out, which matches. This one should have A2, B2, and CN2. A2, B2, CN2. And it should have CN3 coming out and some 2 coming out, which it does. The last one should have A3, B3, and CN3. A3, B3, and CN3. It should have C out coming out and some 3 coming out, which it does. Okay, so that looks like that's set up correctly. And then our last piece of that, okay, I think I got it down here. Maybe. Well, those are 2 RCA 4s. Okay, it's right here. So M0, that's we got 2 RCA 4s here. And we got A3 to A0 and B3 to B0. That's the right here. A30, B30. We should also have CN coming in, which we do. And we should have CN4 going out, I'm assuming, and some 30. Some 30 and CN4 coming out over to here. So we should have A74, B74. So A74, B74, CN4, which is that coming in there. We should have C out going out and some 74. C out, some 74. Okay, that looks right. Or at least it looks consistent with the diagram on that page, I should say. Let's see, the code for add RCA8 illustrates how gate level design in VHDL becomes bulky with decorations and components. Hierarchical design can be made simple if component decorations exploit data flow models at lower levels of hierarchy. For example, a half adder can be designed and used as a component in design of a full adder. So they're just talking about how as you go full down here, where they're talking about the RCA8, it merely is 2 of these RCA4s. And the RCA4 is 4 full adders. And each full adder consists of 2 half adders and an OR gate. And then the half adder, it consists of an XOR and an AND. And then the XOR and the AND are broke down over here. So it builds upon the previous one. For example, a half adder can be designed using a component design of a full adder. That's what's shown here. You got your full adder here, which consists of 2 half adders and an OR. Which is what we had over here. We had 2 half adders and an OR. This is our RCA4 bit adder definition over here, which is 4 full adders, which corresponds with the 4 full adders over here. Now this next topic is a HDL model of 3-state gates. Oh, I don't know where the original picture was, but probably went right by it. But they got pictures down here. Verilog, predefined buffers and inverters. Verilog has 4 types of predefined 3-state gates, as shown in the figure 4.35. The buff if one, this one, gate behaves like a normal buffer if control is equal to 1. And output goes to a high impedance state Z when control is equal to 0. The buff if 0 gate behaves in a similar fashion, except the high impedance state occurs when control is equal to 1. Okay, this is when it's 0, and this is when it's 1 for that one. The 2 not if gates operate in a similar fashion, but the output is the complement of the input when the gate is not in a high impedance state. Gates are instantiated with the statement: gate name, output, input, and then control. Grab another drink. Need lots of caffeine for this stuff. Okay. Gate name can be that of any one of the three state gates in simulation. The output can result in 0, 1, X, or Z. Two examples of gate instantiation are this: buff F1. Here's our buff F1. They don't use A's and B's on the other side, so really can't make the comparison on those. But we have our out, A, and control, and that corresponds with our gate structure over here. Output, input, and then control. So out is our output, A is our input, and the control is our control. And note if 0 is again same principle. So out, in, control. So Y is our out, B is our in, and our control is our enable. First example, out has the same value as A when control is equal to 1. Out goes to Z. There it is. Z is our high impedance state. Okay. So out goes to Z when control is equal to 0. Second example, Y equals Z when A enables 1, and output Y is equal to not B when enable is equal to 0. Okay, so getting into the definition. Here's a definition where we got 3 states. So we're bringing in A, B, and select, and that's giving us our M out. This tells us M has 2 drivers, and this is based upon the definition up there. So it builds. This is a 2 to 1 line multiplexer with 3 state buffers. The if 0 is when you have the inverter on the bottom of this. And you got an inverter out in, well, that's not having it out in front. This one has it in front. Okay, I just have to look it up again. So here's our entity breakdown. Buff in and control. And buff in must be here, control E. And our buff out is equal to buff in when control is equal to 1. So if control is equal to 1 coming in here, then whatever's coming in is also going out. So that's what it's saying. Otherwise, if it control is equal to 0, then we want our high impedance state. Where does it give us the? Then our buff F1, that's, what word's buff F1? This first one here. Oh no, that's what we looked at. Not F1. This one. So we have our input, our control, and then invert there. So those be under wording, but I know that there's nothing special about it. Like when they're talking about the input down here, they're just putting a BUF underscore in to represent the input for buffer. Down here, they're putting the not in front of it to indicate this not if for our entity and architecture description. Okay, so that's just going through and setting those. Okay, numbers in HDL are represented in formats that enable interpretation, specify their size and base. Size of a number indicates in bits the length of its corresponding binary word. The value expresses the number in the indicated base. Verilog, numbers in Verilog are represented by the format in, and then your apostrophe there, and then big B, and then V. N is the number of bits used to store the value. B is the base for interpreting the value, and V is the value to be interpreted and stored. So like down here, the 3 indicates 3 bits, the little b is binary, and this is 2 to the 0, 2 to the first, 2 squared is 4, 6, so that's why it's decimal 6. This is 8 bits. The H, the apostrophe H, represents hexadecimal. A5, this is 16 to the 0, which is 1, so that's 5. This is 16 to the first times A, and A is 10, so that's 160, 165. Yeah, 165 decimal. And that must be what is in binary. And these, if you wonder, well, where do you use those at? One place you see those is if you decide to torture yourself and want to take assembly language, you see those values over in assembly language. And it's just now clicking with me what in the world this number represents. Because whenever I've seen that in assembly language, I'd never have wondered, or I never have figured out what my first number indicates. But that's the number of bits. Okay, let's talk about the Verilog. Numbers in Verilog are represented by format. What is that one we just talked about? We'll talk about that one. Never mind. VHDL is a strongly typed language. The type of assignment to variables must generally match the type of the variable. Most of the variables and examples in this text have a standard logic. Numbers of standard logic are written as binary values, and VHDL requires that they be enclosed in single quotes. For example, the text 0 and 1 indicate binary values of 0 and 1 respectively. Standard logic vector constants are written in the format number base, double quote, value in double quote, where number indicates the number of bits used to represent and or store the value. Base indicates the base of the number, and value is the number to be interpreted in the indicated base. Bases are indicated by a single letter as big B for binary, O for octal, D for decimal, and X for hexadecimal. And numbers not specified in this manner defaults to a binary value. Size is given, number of bits, and the value is used. Oh, okay. No one to blame you if you disconnected. This stuff's just as dry as can be. Do you find this stuff exciting? If you do, then more power to you. Okay. Here's VHDL. Are you back? Okay. This is VHDL. The 3 represents our 3 bits. V is our binary. And then the 110, that's 2 0, 2 to the first, 2 squared. So that's 4 plus 2 is 6. That's where it's decimal 6. Now here we got 8 bits, and X is a hexadecimal. And A5, this is 16 to the 0, 16 to the first, it's 165 decimal. 8 bits, binary, 2 to 0, 1, 2, 4, 4, 5. It doesn't say what it's equal to, but yeah, that's decimal 5. And then when you put 8 bits, what it stores is you have to have 8 bits here. And same up here, you store in your 8 bits like that. Now here, big B and then 010 is just stored to 3 bits as this, since the bits aren't specified. It just defaults whatever it was. And hexadecimal BC. BC. That's in hex. And obviously I don't know what I'm doing there. How do I get H? There it is. So H, 188. Okay, now 188 to binary. So 188, and do my convert. I know I'm cheating here. Just my brain's hurt from all this. So convert, not convert, base, changing that to binary. 1041s, 00. Okay. So this put as many bits as necessary in order to store this hex value right here. B5. I need that in hex, so I go to my base. It's in hex, and I want to convert that to binary. One, two, three, four, five, six, seven, eight. I wonder if I change the 1 in hex to binary. Okay. I was wondering if it automatically put like a certain number of digits, but it looks like it just puts whatever it needs to accomplish the goal. Okay. So they're just introducing you to the notation of how that's represented. Data flow modeling. Data flow models describe combinational circuits by their function rather than by their gate structure. Common form of data flow modeling of combinational logic uses concurrent signal assignment statements and built-in language operators express how signals are assigned values. Verilog has two families of predefined data types, nets and variables, also referred to as registers. The net family includes data type wire, which corresponds to signals associated with structural connections between design elements with implicit combinational logic represented by continuous assignment statements. The variable family of data types distinguished by its members being assigned values by procedural statements and by their retaining an assigned value until a new value is assigned. Keywords of some of those types and families are register, integer, and time. Reg may be a scalar or vector quantity. An integer is the host machine and is at least 32 bits wide. A variable having a type time is represented by an unsigned 64-bit quantity. So again, you can see why they you try to use the smallest data type you can in programming. Verilog provides about 30 different operators. It lists some of the operators in table 4.10. Complete list of operators supported by Verilog 2001, 2005 can be found in the table in section 8.3. So these are ones they support. Your system Verilog assignment operators represented here. That's like that plus equals, minus equals, add right hand side, left hand side, assign, and so forth. And here's your increment and decrement operators: I plus plus, I minus minus, plus plus, I minus minus, I. I'm reading that right. Okay. They talk about how a sign is how you incorporate those in. So we got our and our or in there. Which corresponds to the again logical and over here and logical or. Now data types that are in VHDL, the predefined data types here. We got bit, which is either 0 or 1. Again, think of that as voltage. Boolean, false or true. Integer, and this gives you a range of values. Positive integers go from one up. Huh. Interesting. I would have expected negative be in the list too, but it didn't have negatives. Natural. Natural. You remember what your definition of natural number started with? Way back when you covered it? Natural started with 1. It didn't start with 0. But this indicates that VHDL has natural start in 0. Oh well. Here's your real numbers. Again, other programming languages you hear refer to that as double or float. Your character, little a through z and big A through z, and digits 0 through 9, special characters. And remember, that's over in your ASCII chart where you see those. And time, integer with units fs, ps, ns, us, ms, sex, minute, min, or hr. And we saw this over in ModelSim. Um, maybe I'll try to click on over here. A is U. Open a different project if I have one. I don't think it opened it up. Yeah, that's my one there. Anyway, doesn't look like I'm gonna be able to show it. But remember where it had these like little abbreviations to the side, like NS. This is 0 nanoseconds. We had PS2 and so forth. PS also. Let's see. Bit range of the indices of vector determines the number of bits. For example, A7 down to 0 and B0 to 7. Each hold 8 bits. Indices of an array are integers. An array must be declared as a named object of a named array type. For example, that our opcode is array bit. And our signal arithmetic opcode is equal to this right here. Then our constant code 2 is an opcode equal to that. Somewhere along the line, I missed why they go from 7 to 0 instead of 0 to 7. But that's why they got it defined. Let's see. Arithmetic has type opcode, initialize this. A vector is not initialized, is initialized by default to all 0 bits. Elements of a vector can be initialized individually. If I include them in the parentheses, enclosed comma separated list of values. So the C is equal to, and then they got 1, 0, 0, 1, so forth. Tells you don't have to do this part. Elements of a vector can be referenced by parentheses enclosed index. For example, arithmetic 2 is the third bit from the right. So up here, that'd be 0, 1, 1. So that'd be that 1 right there. Slicing, it's kind of the same principle as we saw earlier. Let me see that. Introduction to or 3D computer animation. Slicing means take a part of it. Contiguous range of elements called a slice can be addressed too. Arithmetic 6 down to 4 is a 3-bit wide subarray arithmetic of arith. The syntax template for declaring arrays is as follows. Starting index to ending index. You got your type, the name of this array element type. Like this right here. We're saying it's a type. The name is called nibble. It's an array from 3 down to 0, and it's of the data type bit. This is a reference, signal nib underscore 1 colon nibble, so it's referencing that. And data underscore word is an array, 15 down to 0 of a bit. Got all excited. There was an additional person on there. um, let's see. Anyway, we got 16 bits here, if I were to count them. $15 down to 12. So when you go 15 down to 0, then this means this far right one here is our 0th, and this far left one is our 15th. So 15 down to 12, 15, 14, 13, 12. That's where the 0011 comes from. And my video's not up now. Okay, predefined operators can concurrent signal assessment. Data flow models in VHDL are composed of concurrent signal assignment statements. Simplest form of concurrent signal assessment statement has a syntax template. Signal name, and then less than or equal to, then your expression, whatever that is, and then if necessary after a delay. Here's our different symbols for like binary logic, and, or, XOR, XNOR, and so forth. Some of these don't make any sense for the different data types. That's for bit up here, Boolean. The relational, the two expressions matched in type and size. So it doesn't matter what it is, as long as they're matched. Here's an array of bits. Vector. Vector is another word for like an array, a list, some sort. Addition operators only work on integers and real numbers, doesn't work with bits. And then we got our concatenation operator for vectors. Miscellaneous and so forth. Here to bus, it's a bit, 15 down to 0, and they're all zeros initially. And for an integer whose value is between 0 and 63, we put integer, C comma D, and then integer range is 0 to 63. So a different way of representing that for integers. Never-ending chapter. Here's a decoder, 2x4, and we have our input coming in, so 2 input, and we have 4 output going out. So that's what 2 by 4 represents. This is the vector. Think of it as an array. So we got D0, D1, D2, and D3. Two coder. Here it is right here. Okay. Here's our 2 to 4 line decoder on page 177. We have your A, B, and E coming in as their input. And of course, we've got inverters there. And then they're going into these NAND gates right here, represented by D0 through D3. And looks like A, B, and E are going into all 3. If I'm reading that right. Or no, like D0 is not A, not B, and not E. D0, not A, not B, and not E. And there's ands between those. And then we have our inverter on the front. Because even though they're going in there, they're being inverted here with that little circle there. Now D1. D1, not A, B, and not E. So not A, B, and not E. D2. D2 is A, not B, not E. So A, not B, not E. D3 is A, B, not E. So A, B, not E, and then our not here in front. Does that make sense on that 2 to 4 line decoder? That doesn't have any gates. I bet we could actually code that. Try. Mainly because I think it might have an error there. And I'm just curious if they do. Okay. Model sim. Okay, do a new project. Close that. And this is a Verilog. And a 2 to 4 line decoder. Create a new file. It's going to be a Verilog. And test, what's the .b, I think. If I remember right. Path name already exists. .b. It's the problem with saving them all in the same folder. Okay, double click that, get that to come up. Got a module encoder 2x4 df. That's the beginning parentheses. Output 0:3. It's our D. Input A, B, enable. Assign D0 equals exclamation, exclamation A and exclamation B and exclamation enable. I think that's comma. D1 equals exclamation, beginning parentheses, exclamation A and B and exclamation enable. And D2 equals exclamation A and not B and enable, not enable. D3 equals to exclamation A and B and not enable, semicolon, and module. Save that, compile it. Oh, I guess it did compile. Okay. I saw the space here in the book, and I didn't think that should be there. But I guess it doesn't matter if you have a space there or not. Never mind then. I'm gonna stick with the Verilog. The VHDLs kind of make me tired. It's just so wordy and it's just not as clean as the Verilog. HDL's kind of cumbersome too. I don't have a Verilog breakdown. Or no, this is Verilog. Okay, so 4-bit adders. 4-bit adder. Here's 4-bit adder. Okay, so input A, B, C, N, and A and B 30. Binary adder Verilog automatically accommodates additional words even though they have different sizes and are strictly speaking of different types. Hmm. Data flow. Well, I don't see exactly how the definition works, but what it's doing is you got your two inputs here, A and B, and then your CN. And A is going from 0 to 3, and so is B. And your CN should be the values coming in here. But they don't accommodate for them being four of them. So that's part that's a little bit confusing to me, but doesn't specify anything about it. So can't elaborate on that. And then C out is these values coming in here for your C out, which again isn't a single item. It's more of an array. And then your sum is the ones coming down here. Then the operations being done here is we got a plus, an or between them. And then that's giving you not only a sum, but it's giving you a carryover too. I guess I'm expecting recursion or something where it's or some kind of looping construct where it calls itself. I mean, it handles itself because you're not putting A0, A1, A2, and A3 here. It's just taking the A, that entire vector, and bringing it in. So it throws me a little bit on what the sign is doing exactly there, but the rest of it makes sense, more or less. There's our 4-bit comparator, and that's nothing more than having these less than and greater than here, returning true or false. And conditional signal assignment, multiplexer, 2-to-1 multiplexer. Two-to-one multiplexer. That there. Verilog. Input, 3 inputs, A, B, and a select. Then our output. There's our select coming in down here. And here would be our A and our B. Here, but assume their code's right. M out, and then you got your select. That's coming in. That's your input. And depending upon whether that's 1 or 0, it either brings back A or B. That takes us to 4.13. And that's probably not a bad place to stop.